Okay, so I'm going to go a little bit slow initially, and then we will see what we can do in this 1 hour. So the work that I mostly do is on something called random laser, and which is also the title of this talk. Controlling the emission properties of random laser. So this is slightly, I would say, a loaded title. So we have to go slow. We have to understand what is emission, what is laser, what is random laser, and so on and so forth. We will go into that. Before that, let me tell you, I'm working here as an assistant professor in the physics department. I joined here about 7 8 months back, so I'm also new here. Uh, and a little bit of my background. I did my PhD from Tata Institute of Fundamental Research, TIFR Mumbai, in the Department of Nuclear and Atomic Physics. And Professor Sushil Majumdar was my PhD supervisor. So today, the work that I'm going to discuss are mostly done in this lab. Okay. Then for a couple of years, I was at European Laboratory for Nonlinear Spectroscopy. This is in Florence, Italy. And then I came back to India, got the DST Inspire Faculty Award, and joined IIT Kanpur there. IIT Kanpur, and there I worked as a DST Inspire faculty for about 4 years before joining here. So tomorrow's lecture will be the work that I did here, and today we are going to discuss something that I did during my PhD. Uh, okay, so before this, let me ask you something. Okay, that how many of you are familiar with the word laser? Somebody can say yes, no. At
Yes,
least
sir.
you have heard laser, right? So
Somewhat,
what?
yes.
I'm familiar.
So,
Right.
yeah, very
Yes.
good, very good. Yeah. So what is laser? By the way, can somebody just extend this name, LASER, for me?
Live amplification through simulated emission of radiation.
Very good. Yeah, correct. And have you also heard something called mode of a laser? What is mode? Mode? No, nothing. Fine, it's okay. What's about scattering? Scattering, I guess all of you have heard. What is scattering?
Yes,
When
sir.
light and yeah, when light encounter any particle, then there's scattering and so on and so forth. But have you heard about Rayleigh scattering?
Yes, sir.
Okay, you have heard, right? And what's about me scattering?
No, sir.
No, sir. Strokes and
Me
non.
scattering, you have not heard. Yeah. So I mean, why the sky is blue, right? That is because of Rayleigh scattering. This is something that I guess all of you know. But suppose somebody asks you why the clouds are white. Okay. So that is because of me scattering. Fine. Another thing, I guess all of you has heard about what is photonic crystal. Have you heard about this name, photonic crystal, earlier?
No, sir.
Okay,
No, sir.
photonic you have not heard. Fine. So all of this is kind of giving me some background, some input from you, so that I can kind of tweak my talk. What's about cavity, optical cavity, something like, let's say, Fabry Parrot mode or Fabry Parrot cavity, let's say, not mode.
No, sir.
No,
No, you
sir.
have not heard. Very
So
good.
right,
No, sir.
optical and cavity differently.
Yes. Yeah. Repeat again. Sorry, I did not get it. Just repeat again.
सर कुछ नहीं सर ऑप्टिकल अलग पता है कैविटी अलग पता है मतलब दोनों का
Ha. Correct, correct, correct. Okay. And okay, so actually everything is kind of bits and pieces. So, but all this name we are going to take in this talk. So that is why I just want to get the feedback from you guys whether you have heard or not, and then we will begin. So another thing is. Uh, because you have heard about laser, then of course you have heard about light. So what we are going to discuss in this talk, along with the topic that I mentioned, the interaction of light with some structures. Okay, so you have light, you take this light, you shine on a structure, okay, then what happens? This is what we are going to study, okay, both fundamentally and then look at its application and so on. The thing is, I wrote interaction of light with, and then I stopped because uh, with structures. So this structure that we are going to discuss, that can be periodic structure or it can be random structure. Okay, so this is the plan of the talk. But of course, we will go a little bit fast because I have to introduce about this thing also, about my research. Then there's one more thing. You have exam, right? You have this ET exam, and for this you have to answer few questions. So the thing is, I'm not going to ask anything from my research because it may be too much involved, and it will not be that easy for you guys to kind of go through it. So what I will suggest you, so there's a homework problem that I'm going to give you in this, and that is about, so this is your homework. You have to just read, okay, about helium neon laser. And in your exam there will be few questions, I think 4 or 5 questions, which I have to prepare. So I will prepare from this homework that I'm giving you, and you have to read about argon ion laser. Fine, because this will make your life easy. Is that okay? Yes, no?
Yes, sir. Yes, sir. It is okay.
Yes, sir,
Fine.
that's fine.
Yeah.
But about these, I have a question about this. There's abundant amount of information about these two lasers, argon ion and helium neon laser. So
Yes.
how how do we decide? I mean, what's important and what's not important, and what should we focus on? Because there is no material given to us, right? So we have to study from the
Well,
internet or various books.
yeah, so about helium neon laser, about argon neon laser, there are, I mean, of course, if you're talking about materials, then materials you can find in any standard book. Uh, so look for any standard book on laser, like Sigman, for example, or Swelto, or even basics books. I mean, these are standard book, but you can look at basic book. Now what you have to learn is, well, what kind of levels are there, what kind of broadening are there, at what wavelength they are, what is the mechanism, how they function, etc. and etc. Okay, so all the basics things, I'm not like
Okay, so
kind
the
of telling you to
basic functioning, basic
exactly
functioning of these
various kind
lasers.
of, yeah, various kind of broadening, what is the line width of these laser, how they function, and so on. Fine.
Okay, okay, yes, sir. Thank you, sir.
Okay, so yeah, this is the outline of the talk. Now let us start. First, I'm going to discuss what is random laser. Then, because now it is obvious that laser is something, because as one of you said, like it is light amplification by stimulated emission of radiation. So I hope that at least basic things you know about laser. Then I'm going to discuss what is random laser. I will talk about their properties. Okay, for example, what kind of fluctuations are there. Uh, Basically, I will talk about frequency fluctuations, and then I will talk about what is our contribution in this field. And for tomorrow's, I'm going to continue from here and discuss how we can achieve efficient lasing, and finally an application of this work. So let us, how do I go to the next slide? Just a second. Maybe like this, no? Then what I have to do is, sorry, let me see. Let me just say enter. A laser, basically, if you look at the construction part, then it is made of three component: a pumping source, a gain medium, and a well-defined cavity that is made of highly reflecting mirrors. Okay, so if you look at the functioning, the pump is there to excite the atoms. Okay, For example, in case of helium neon, there's helium neon atoms, which are again four level system. So the pump is there to kind of get the population inversion. Fine. So pump is there to invert the gain medium. Gain medium is something where the phenomena of population inversion takes place, and then you have this cavity, well defined cavity. Now this cavity, it decides at what frequency the lasing is going to occur. Whenever you have a cavity, right, then the length of the cavity decides the mode. Okay. And the condition is given by 2L equal to n lambda. Now all of this you will learn when you will go through the helium neon laser. Right? So this formula implies that there are certain wavelength which can stay inside the medium. All other wavelength cannot stay. Okay, only few wavelength can stay in this medium. These wavelength which stay for larger time, for larger duration, they are called the mode of the cavity. For example, here I have plotted for a given L, I have plotted the mode of this cavity. That means only this wavelength can stay inside the medium. Now, whenever there is gain, then what happens? So first of all, like we say, well, mode, but then the thing is, these modes have some quality factor. Quality factor is decided by the width of this spectrum. So quality factor is something that decides how much energy a mode can sustain, or in other words we can say that for how much duration light can stay inside the medium. Now it is obvious because this is an inverted system, we have pumped the whole system, it is inverted. Now if the light stay for larger time inside the media, then of course it is going to amplify more. And now what we do is we just keep increasing the pump. So if you keep increasing the pump, then at the output the light will initially, so this is the output light, it will initially increase slowly, and then what happens is at a certain pump power which is known as laser threshold, the output shows a rapid growth. At this time, this bandwidth that you see here, it just collapses. Okay, so you will have very narrow emission, and this is the lasing emission. So along with coherence, coherence is also one of the important property of a laser. So along with coherence, bandwidth collapse, rapid growth, these are all the characteristics of a laser. Now when the laser development started, okay, so this is like, I mean, from the early days of laser development, when the development started, then there was question, well, what kind of cavity should we decide? uh, why is, oh, and by the way, this is called the Fabry-Perot cavity. Okay, so two parallel mirrors keep at certain distance are called the Fabry-Perot cavity. Fabry-Perot cavity. Okay, so when all this development started, then people started asking, what kind of cavity should we fabricate? And is it possible not to have Fabry-Perot cavity? Can we have different kind of cavity? Still, can we have lasing emission? For example, you look here, this is a cavity wherein one of the wall of the cavity is rough. Okay, in that case what will happen? So earlier, if you launch a light will make some stable resonance inside this, and because one of the mirror is leaky, it is not 100% reflecting, because we have to get something out, therefore we cannot make both the mirror 100% reflecting, because it will keep stay inside. So therefore one of the mirror has to be leaky so that you get some output, right? So here what happens is, like, if you make one of the surface reflecting, in that case what will happen? Light will come, it will hit, and it will make a random path, and then it will comes out. So the question was, can we get lasing out of this system? This is another system. This is a circular cavity wherein the internal wall is rough. Okay, so in this case what happens? You send a light, right? It will make some random scattering, and then it will come out. If you put gain inside this, can we get lasing output? This is the question that people were asking. Now the third schematic is, you have some scatterers, okay, some particles like Rayleigh scatterers, Mie scatterers. So let me just go back here to the definition of Rayleigh scattering and Mie scattering. So Rayleigh scattering is like Rayleigh scattering happens when your particle size, okay, that is smaller than wavelength. So this is something that you have to remember. So particle size, let me say, well, d is the diameter of, let's say, particle, then d has to be smaller than wavelength, the wavelength that we consider. In that case, we have Rayleigh scattering, and Mean scattering is something when my d, or the diameter of the particles, become larger than the wavelength. Okay, this is a rough approximation, but this is what we have to remember. So I ask you, like, why the sky is blue, and then I ask you, well, why the clouds are white? Okay, and I said, well, this is because in one case you have Rayleigh scattering, in other case you have Mean scattering. In the cloud, you have to at least remember this, that the droplets, or whatever, this water droplets that are there, they are larger than the wavelength. And when I say wavelength, which wavelength? The visible wavelength, because that is where we can see. So they are larger than 500, 600, 700 nanometer. Okay, therefore Mean scattering is applicable there. Okay, so now let me come back here. So this is the same scenario. You have to connect everything, all your knowledge that you have. So we have these particles here. These are small particles. Right now they are Rayleigh particles. So it's like, dust particle in air and so on. And we have light. Okay. So light is getting scattered inside this. And of course you have gain medium. Okay. Then people ask, gain medium means you have inversion. Okay. Then the people ask, in this case, can we get lasing? So this was in 1968. Litokov, he's a scientist here, he formulated this problem mathematically and solved this diffusion equation. And he showed that in this system also, okay, so you have amplification. For example, you can think of it as if these are helium neon particles, or any other particles which has gain, which has 4 level, and wherein you can conceive, you can get inversion. Okay, so you have gain medium, and you have this randomly distributed particles. Okay, and you pump the system. Fine, you pump the system so that you have inversion. In that case, can we have lasing? This problem he has formulated here, and he showed that indeed, yes, you can get lasing kind of emission from this open system once the gain, which in this case is proportional to the volume, because your gain is inside this, right? So as you increase the volume, the gain increases. So if your gain, which is proportional to the volume, is larger than the losses. So when I say losses means, photon can leak through. So where they can leak through? They can leak through the surface. So if the gain, which is proportional to the volume, is larger than the losses, which is proportional to surface, in that case we can indeed get lasing out of this open system. And later this is called random laser. Up to here, like, can you understand this part? Yes, no, Hana, something? At least the concept,
Yes,
the
sir.
problem that we are formulating. Okay, fine, thank you.
Yes, sir.
So let me define what is a random laser. At least what it consists of. So a random laser, it consists of a gain medium. Gain medium is what? You can think of as if helium neon gas. Okay, it consists of a gain medium and randomly distributed scatterers. That's it. There's no cavity. There's no well-defined cavity in this case. So scatterers can be dust particle, for example, as I said, like in atmosphere you have dust particle. So here let me call them dielectric particle, because dust particle is also dielectric particle. So scatterers can be dielectric particles. They can be metallic particle also. And what's about gain? I said it can be helium neon, it can be ND doped powder. Now, ND is a different kind of lasing material. Maybe you have heard about, I don't know, ND YAG laser or something like this term or not. But again, these are all of these are gain medium. And then there's certain dye, okay, which you can mix in some liquid, for example, alcohol, and they also have very high emission cross section, and you can get lasing out of these. Okay. Similarly, there are fibers which can latch. So the thing is, there is no constraint what the scatterers can be. Scatterers can be anything. Similarly, there are variety of gain materials that are available. Now let me go back here. Okay, so here we have a cavity which is well defined. Its modes are fixed. All right. Therefore, under inversion, under pumping, whenever the lasing happens, it happens at this frequency, right? Because these are the wavelength where photon can stay inside the medium, right? Here, is there any constraint? Like which photon will stay for larger time? Is there any constraint? There's no constraint, right? I mean, these are random scatterers, photons are there, and of course they are making all this random walk and so on. So which photon will stay inside the medium for larger duration? There's no constraint, okay? Therefore, at any frequency, lasing can appear. Unlike earlier, earlier there was a fixed mode, okay? They were decided by the length of the cavity. When I said 2L equal to n lambda, my L is fixed, therefore this lambda is fixed. But now there's no L because this is random system. I mean, this is one mode, this is another mode, this is another mode. So there are thousands of modes. Therefore, lasing can appear at any wavelength, and this is exactly what happens in the experiment. So here what you see is two spectrum. Well, the term is spectrum only, so there are two spectrum, and you can see here red spectrum and black spectrum. These are two emission spectra from the same system, and you can see there's lasing at this wavelength in one case, but in the other case there's no lasing here, there's lasing at this wavelength, right? So let us look at so from this observation, just by looking at this spectra, what we can conclude is, we can conclude this system, the system that we have in hand, we have multiple peaks, right? Earlier we have one peak, now we have multiple peaks, right? For example, this is one peak, this is one peak, this is another peak. So the spectra consist of multiple peaks. Second, these peaks that we see, it fluctuates, right? It fluctuates from one spectrum to other spectrum. So there's a fluctuation, and this fluctuation is both in wavelength, of course it fluctuates in x-axis, and it fluctuates in intensity also, right? So the next thing is, if we make the distribution of this peak, like at between which wavelength to which wavelength they fluctuates over a range of about 15 nanometer. And let me say that this 15 nanometer is not some holy number. This is decided by the width of the gain medium. But what is important is these two parts. The right hand side that I show here is just quantification of this intensity fluctuation. Now, for various application, we want to control, this fluctuation that is there. The thing is, how do we control this fluctuation? So let me not discuss this part right now. It's already 30 minutes into the lecture, so let us not discuss this part, and let us directly come to this part. Okay. So one way to control this fluctuation is by, so earlier I said that these particles that I have, okay, it is not necessary that they have to be spherical particle. They can be of any shape, any size. One proposal was, what if we make these particles spherical? Okay, and not only spherical and same size. Okay, so this is called resonant scatterers. That means the scatterers are of same size. Okay. And when the scatterers are of same size, and let me see here, the size of, so this bar is 5 micron, okay? So they are about, the diameter of the particles are about 1 micron. That's okay, it's already written, fine, good. So it is already written that the diameter of particle is about 1 micrometer. Now, the wavelength that we are interested in is about 500-600 nanometer, right? So here, let me just point out that the wavelength is smaller. Lambda is smaller than diameter. So can somebody say what kind of phenomena is going to take place? Is it going to be Rayleigh scattering, or is it going to be Mie scattering? Anyone? Yes, no?
I think so. Mie scattering.
Yes, correct. So there will be Mie scattering. Why? Because the wavelength is simply smaller than the diameter. Okay. By the way, Rayleigh scattering is the approximation of Mie scattering only. So For exact calculation, you apply me scattering, and then you take the limit. Okay, that now my lambda is much larger than the diameter. Then you approach to the Rayleigh scattering. Fine. So me scattering gives you correct and more precise scattering cross section. So here, yeah, so here you are correct. Me scattering is
So,
going
so
to
in the so in the case of relay scattering, also we assume that the laser is going under, the particles are going under me scattering, and then we do the calculation.
that is how you do. No, I mean you are asking me or
So I'm asking. You.
I see. Okay. No. So Rayleigh scattering. So Rayleigh scattering is treated separately. What I am saying is, me scattering gives you the exact answer. You take me scattering, all right, and then you apply the limit that your lambda is smaller than. I mean, your lambda is larger than the diameter of particle. In that case, you can get the results of Rayleigh scattering. Fine. But in Rayleigh scattering, as far as I know, you assume that the particle size are like already, I mean, you take them as point particle or something like this. I mean, you assume that the particle size is for sure larger than the wavelength.
Okay, sir.
I mean, smaller than the wavelength. Yeah. So here the phenomenon of me scattering is going to take place. So these are the profile. Profile in the sense, these are the scattering profile of a single particle. Now, what does this say? This say that I have a collection of these spheres and you send a light. So let's say I send a light like this. By the way, this is a 3D sample, huh? And we are in 2D right now. So let's say I send a light like this. Okay. Then at these peaks, light is going to experience more scattering, right? So that is the meaning of this curve. So you have total transmission. So the transmission increases and decreases. So wherever you have peak, that means there's more scattering and so on and so forth. So you send a light here, for example, let's say torch light. You send a light will perform all this scattering inside this and then it will come out, right? So in the output you have this kind of spectrum. This means that at this wavelength light has scattered more. Okay, now I will ask you, if the light will scatter more, that means what? That means the light has stayed for larger time in this sample, right? Because it is experience, because every particle is scattering the light more effectively. That means if I look at the time distribution for how long light stays inside this medium, then you will find that there are certain wavelength, right? These wavelength for which the light will stay for larger time. Now I will ask you, if I put gain inside this, if I put amplifying medium inside this, then what will happen? Then at those wavelength, right, which stays for larger time, you will have larger emission, exactly like a laser. And this is what they have reported in their work, that at these peaks, there is more intensity. Okay. Moreover, by changing the particle size, this D, you can change the resonances, and therefore, where this lasing is going to appear, that also you can change. Fine. This part, anyone?
Yes, sir.
Okay, fine. So we have this is something that we already know. When I started my study into this field, then all of this was known. Now we ask some fundamental questions and basic question about this sample. Question number one. So if you are more interested, then you can read this paper, but it is a computational paper, so up to you. So yeah, so we ask the following question. Now you have these scatterers which are spherical, fine, and you said, well, if they are spherical particles, then of course at the resonance we have more scattering, therefore the lasing, etc., it will appear on those resonances. Now we ask, so where should I put my amplifying media? Should I put the amplifying media between the particle, or should I put the amplification, the dye, right? I'm talking about the gain medium, that means the helium neon. I mean, you can think of it as if this is helium neon. So we ask the question that should we put gain between the particle, or should we put that amplifying media inside the particle? The first one is called inter-scatter gain. That means the gain medium is present between the particle. This is called intra-scatter gain. That means the gain is present inside the particle. Okay. Now we consider slightly larger particles. Therefore, it is more into the Means-scattering regime. But by the way, these are the spectrum, the transmission spectrum. And again, as expected, at this peak, we expect lasing emission, and this is exactly what happens. So this is for the first system wherein we have inter-scatter gain, and for the intra-scatter gain, the situation is like this. Now, just from the visual inspection, let me ask you, which one is better? Better in the sense that which one is more closer to a laser? This one. So let me call this 1. Let me call this 2. Which one more looks like the spectrum of a laser? So a laser is defined by something which gives you single frequency, single wavelength, intense signal. Anyone can guess? Say.
That case one would be better.
Case 1 will be better. Let me again show you the spectrum. So this is the spectrum of a laser. So something like this. Okay, single frequency, single wavelength. Right. So of course, I mean, both are good. It depends how you look into this, but there are certain observations that we can make. Okay, here in the first case, there are many peaks, and if you look at the spectrum, almost at every wavelength, we have some emission. Okay, so we have one peak here, we have one peak here, and then there are all these small peaks. So right now we have not increased the pump power much, but we are kind of near the threshold. Anyway, you can see that there are many peaks. In this case, there is only one prominent peak. Okay, then we traced why this is happening. So what we did was we calculated the lifetime of photon. So you send a light, and then we see for how long a photon can stay inside this medium. Now note that these are not Rayleigh particles. These are Me particles, and Me particles do two kind of scattering. So now let me come here. Let me just discuss here. So in Rayleigh scattering, you have, let's say, point particle. You send a light, light will get scattered. In Rayleigh scattering, what happens is, of course, you send a light, then light will scatter. Apart from that, light can also stay inside it. Okay, so you have a particle here, light can stay inside this, and apart from that, it can also scatter. So there are two phenomena that can happen. One is light can scatter from the surface. Another thing is light can make a resonant, it can stay inside the particle resonantly. Because of this, okay, because of this phenomena, in the second case, when we put gain inside the particles, then light stays inside this, and you have gain, right? So therefore, what happened is you have more prominent lasing. So now what we have assumed while doing this calculation, we have assumed that number one, all the particles are spherical. Okay, and our calculation shows that once we have gain inside the particle, then we can have better lasing. Now this is theoretical calculation. I ask you to do experiment on this. So it is not that easy to get big particles wherein all the particles are of same size, and then you compare what happens when you have gain inside one particle and when you do not have gain inside other particle. Such kind of experiment is extremely difficult. That is fine that we have done the calculation, and our calculation shows that of course this system is better, but experimentally it is not very easy to conceive it. So what we did was we consider, well, let us make the particle bigger. Okay, so this time we consider a particle size of 3.5 micrometer diameter, and making dielectric particle spherical is difficult. But if you take drop of water, okay, then because of surface tensions, they become spherical. Very easy, they become spherical. If you send the particles in let's say in air over some distance, then you will see because of surface tension they become spherical. And of course, there is a way to make all of them monodisperse. So when I say monodisperse, I mean of same size, same diameter, etc. So we consider a situation wherein the particle size is 3.5 micrometer. So you can consider them as micro droplets. Okay, and the gain is inside this. The amplifying media is inside this. So you can think of it as if your helium neon is inside this and you have this scatterers. Fine. Now this is the scattering profile. Scattering profile means at this wavelength, you send a light at this wavelength, the scattering will be more prominent. At this wavelength, the scattering will be less prominent. Fine. So again, we expect that if the scattering is more prominent, that means light will stay inside this system for larger time at this wavelength. Therefore, we expect lasing at this wavelength, and this is exactly what happens. So if our systems are monodisperse, that means all the particles, so let me just draw it once again, we have all the particles that are of same size. That means that this resonance that we have here, it will be same for all the particles. Okay? It is same. So all the particles scatter at same wavelength. Therefore, at this wavelength, you have lasing. Now, once you make the particle polydisperse means, let's say, one of them you make big, one of them you make small, big, small, etc., etc. In that case, this resonance that you see, right? That resonance. So for one particle you have this resonance. For other particle you have different resonance. For third particle you have different resonance. And we are looking at the collective phenomena. That is the phenomena of the whole system. Then just some of them will be flat. Okay. Therefore, if we make them polydisperse, in that case, there is no preference, so the lasing will appear at all the wavelength, right? And of course, all of this we cannot say based on one spectrum. So what you do, you look at collection of spectra. So for example, this is the histogram. Histogram means the distribution of the peak over 100 spectra. And you see that when the particles are monodisperse, okay, same size, gain is inside, in that case the lasing will appear here. And if you make them polydisperse, then they appear over a range of about 15-20 nanometer. Is this part clear to some of you? I mean, I'm not expecting to learn everything, but at least this concept is clear to me, like what we are doing. Otherwise, it will be very boring if you don't respond. Huh? Yes, no, you can at least understand the story, no? Like how it is going and what is happening in the system, etc. Yes, no, anyone?
Yes, sir.
Okay,
Yes.
fine. Yeah. Now let us come to the experiment. Okay, after doing all these things, so first let me tell you what we have achieved so far. We said we have a system, right? Inside this system, we have spherical scatterers. Okay, and point number one, based on the calculation, okay, based on the calculation, I said that if you make all the particle monodisperse, that means of same size, and you put gain inside this, then it can give you lasing at fixed frequency, and the lasing will be better. When I say better, I mean I am comparing two cases, whether you put gain here or you put gain between the particle. Okay, so number one, gain means amplification, your dye or your helium neon particle, etc. Gain inside means inside the particle. That is one thing. Second, if you make them monodisperse,
Gain inside
yes,
mean like what do you mean by gain inside? Means like
inside
what
the particle. Okay, so let me just
inside the
write here.
particle, not able to understand it.
Sorry.
Means you are putting inside the particle. I'm not able to understand it. Like gain is also a physical entity. So how are you putting it inside another particle? Means like,
Yeah, okay. So let us look at the experiment then. We are going to discuss the experiment now. So first thing is we put gain inside the particle. So what is gain? Yeah, so fine. So as I said, gain, when I say gain means something for level atom, right? For example, helium neon. What is helium neon? It is a vapor. Similarly, you can have molecules, you can have dye molecules. Okay. So dye molecules, And by the way, they are extremely small. They are kind of nanometer size. If you look at the particle, they are kind of nanometer size particle. Okay. So yeah, so this is the question, that how do you put gain inside the particle? Yeah, this is a good question. And we are going to address in this slide only. So first of all, let us understand what is gain. Gain are these molecules which have 4 level, wherein you can pump it, you can send them from ground state to higher energy state. So you have all this, schematic of the laser, right? You have this ground state, you have excited state, and then you have whatever this meta stable state and so on. So these are molecules, right? You send light on this molecule, they will go up, they will settle, then you will have population inversion, and they will kind of populate, and between two populated level you have lasing emission, right? So by the way, I mean, all this is good for schematic, but in reality they are particles, right? And they are kind of, nanometer size or tens of nanometer size particle. Fine. And this is something that is big particle. These are me scatters, so they are kind of 10,000s or even more times bigger than these amplifying molecules. Okay, so what you can do is you can, so for example, yeah, so let me show here what I do. Okay, so this is gain inside particle, and second is monodisperse. That means all the particle I have to make of same size. Okay, now what we can do is we can take water, right? Inside this water droplet we can put these molecules. So we can take them, mix with water. It's like, mixing color. In Holi you have dye, right? This is the same dye, but of course you can have population inversion in this. Okay, so they will look literally like that. So you have water, you mix this dye molecule into the water, and that is your amplifying media. Okay. Now we have to create droplets out of it, and we have to create monodispersed droplets. So what we did was we take this water and amplifying media, we pass it through a capillary, and of course we slightly pressurize it so that you have a stream of it. Now you can think of it as if you have a tap and water is coming down, and you pressurize the tap so that you have a stream of water. Fine. So we have, and to be precise, we do not use water, we use alcohol, that to like ethanol, because of certain reason. So the reason is, well, the quantum efficiency of the molecule that you have, that is larger in ethanol compared to water, but again it's a separate thing. So you can think of it as if this is water. Inside the water we have this amplifying molecules, we pressurize it through a thin capillary, and when we pressurize, then we have this drop of water that is coming out. And in this capillary we also have a piezoelectric gate. Okay, what this piezoelectric gate do is, so you have this liquid which is flowing, then with the piezoelectric gate we chop this. Okay, we cut the stream at regular interval. So when we cut it, it creates a perturbation, and therefore we have this droplets. Okay, and by tuning the chopping amplitude and the chopping frequency, we can control the size and spacing between the droplets. Okay, all of this we can do in the experiment. So in the first case, okay, we do not chop at regular interval. Okay, that means the system is completely irregular. So in that case we have polydispersed droplets, as you can see here. So this is the actual experiment, by the way. Okay, so we have one droplet here, one droplet there, one droplet there. So all this is amplifying media. Okay, the gain is everywhere, and these droplets are made of alcohol, water, whatever you can think of. Now let me ask you, okay, by the way, this phenomena that you see here, okay, all this phenomena, this phenomena, this phenomena, this is not a single particle phenomena. Okay, this is like, we are not studying scattering from a single particle. What we say, you send light, it makes all this scattering, right? And then the light comes out. What is this? This is a collective phenomena of the system, right? Wherein all the particles, etc., they takes place. They participate in scattering. Now let me ask you, we want to see some emission from this. In which direction should I see? I mean, in which direction we have collective effect of all the droplets? In which direction should I see? So you have this system, and I'm asking you as a student that I want to see collective effect, wherein all the droplets, all the emission from all the droplets takes part. In which direction should I look? Anyone? Yes, no?
Sir, please repeat the question.
Yeah, so my question is, okay, so let me just go back to this problem again. So I have these particles here. Okay, so this is typical random laser concept, the one that we have discussed earlier. And I send a light. This light gets scatters from all the particles and then it comes out. My thing is that this is a collective phenomena. Collective phenomena in the sense that all these scatters, they takes part into scattering. Right? Here I have a system wherein the particles are like this, and I want to look at the collective phenomena wherein all this particle takes place. A phenomena wherein all these particles take part. So in which direction should I see? Of course, I should look in this direction
Upside.
only. Yes, exactly. So I should look, I mean, the signature of anything, I mean, of lasing, etc., anything. I should look only in this direction because that is where, all the particles can participate in scattering. Otherwise, if I look in this direction, then, only single particle will participate. So therefore, what we do is we place a mirror here at 45 degree. So what this mirror will do, whatever emission is taking place along the droplet, it will just redirect. It is at 45 degree. It will redirect towards the spectrometer. Okay? And then we can do the spectral analysis. Okay. So by the way, before this, let me characterize our system. So how do I characterize this system? The only thing that I have is size and spacing between them. Okay, right? So we can look at the size distribution. This is the size distribution. The size of particle is about 20 micrometer. Okay. The earlier study that we did in the calculation, we consider the particle size of 3.5 micrometer, and in the experiment we were able to make particle size which are about 20 micrometer. And of course the spacing between them is completely random, as you can see here, and it is also obvious from the figure, but you can make the distribution by looking at various uh, droplet systems. So now this is the spectra. Okay, so let me just tell you what is happening again. We have these micro droplets. All of them are a random size. Spacing between them is also random, right? And we excite it with the pump. Okay, so you send light on this. The atom inside the droplets will go into higher energy state, upper energy state. Then one of the photon will come down and it will stimulate other atoms to emit in the same channel. When I say same channel, I mean the same frequency, same wavelength, same polarization. So this emission is happening in this direction. We put a mirror here and we look at the signal. Right now, first thing, gain is inside. As I already discussed, this is good, but the particles are not of same size. That means their resonance will be at random wavelength. So if I sum them all, then what will happen? I will get a flat curve. Okay. And this should reflect into the spectrum. What do I mean by that? Well, I mean that if I look at the lasing frequency, it will appear everywhere, right? As it happened here, because the particle size is not uniform. So therefore the peak will be everywhere, right? This is exactly what happens. If I look at the distribution of the peak in one spectrum, peak is here. In other spectrum, the peak gets shifted. And if I plot the distribution of all of them, they appear over a range of about 15-20 nanometer. Okay. So this is like a typical one-dimensional random laser. Now, let me discuss one more result and then maybe, so you have class after this? Anyone?
We don't have a class, but we do have some means
Other
some
obligation,
students
fine.
have some other obligations.
Yeah,
Some
fine,
other.
fine. Yeah, okay. Okay, fine. I will not stress much. But one more result. So now, in the next step, we make this particle monodisperse. When I say monodisperse, all of them are of same size. Now, in this case, what do you expect? If the particles are of same size, in that case, we expect that the resonance will exist, okay, and the lasing that is there, it will be on those resonances. This is exactly what happens when you make the droplet monodisperse. As you can see here, this is done by the piezo that I discussed earlier by chopping at the same frequency. In this case, you can see here the lasing appear in some bunches, uh, but more or less they are at same wavelength. And of course, we cannot conclude this based on one spectrum. So we look at the distribution. In the distribution, you can clearly see that lasing is only at certain wavelength. Now, the other point is, how do we decide the wavelength? Okay, so well, the wavelength is. Can anyone comment like what decides at what wavelength this resonance will appear? Based on the story that we are discussing? Yes, no? Is it obvious that it will depend on the particle size on this D? Is this part obvious? If I make the droplets, if I change the particle size, then this resonance will shift. At least this part is obvious to you.
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, fine. So yeah, so this is exactly what happens when you change the particle size, then this resonance shifts. But now, before doing anything, before doing any further analysis, anything further on the system, we have to know what is the particle size. Only then we can do something, right? I mean, if we don't characterize our system, then we cannot say anything about the system. So the next thing is how to find out the particle size or the size of the droplet. Let me repeat again. You have a system, droplets are falling down. On an average, the droplet size is about 20 micrometer. But I have to do further analysis. For that, I have to find out what is the exact size of this particle. Okay, so how do we find out the exact size of the particle? Number one, I can go back to my experiment and I can see, I am flowing the liquid inside this. So there is a flow rate. Then these droplets are coming from a thin capillary, so its diameter, viscosity, etc. All this will decide what is the particle size. And based on the literature search or by developing a formula, I can find out what is the particle size. And it is exactly what is done here. We have the flow rate, we have the chopping frequency, and I can find out the diameter. But you have to note that the flow rate, do we have do we precisely know how much liquid you are flowing inside the capillary? We do not. So therefore the estimation that this will give me is not exact. It will only be approximate, which we do not want. We should know exactly what is the particle size. Only then we can make further characterization. So for that we go to the spectral technique, and again for that you have to know little bit of optics. That if I have a resonator or some particle, sphere, etc., I shine a light into this, then light can go under total internal reflection. Have you heard about total internal reflection? TIR.
Yes, sir.
Okay, so what happens is when the incident light is more than certain critical angle, in that case, light can stay inside the sphere, and the advantage is we have gain inside the ball, we have the dye inside the ball. So what will happen at that wavelength? We will have larger emission, and this is the experimental part. This is my x-axis wavelength. Okay, at this wavelength we can see here I have larger signal, I have larger signal. These are those wavelength wherein the total reflection takes place. Okay, and the frequency of these will be decided by the particle size, and we can do the back calculation and find out the exact particle size. So again you can see here these red one are the calculation, and this blue curve that you see here, these are the experiment. And based upon the spacing between the peak, position of the peak, we can find out the exact diameter of the particle. So now we have exact size of particle. By imaging we can know what is the spacing between the particle. And what other observation we have? We know that the lasing phenomena is happening only along the droplets. Fine. So now we can model our system. I will not do the modeling here. I will not do the modeling right now. For this, let us wait for the next class. Fine. Should I stop or you want me to continue? Because up to you.
Thank you,
I'm
sir.
free.
Thank you, sir. Thank you very
Okay.
much, sir.
Okay.